everyone, today we will go through the earthwork related to the route surveying. In route surveying, the earthwork consists of two components. The first one is the movement of the materials from the other places to the field to establish a predetermined surface for the construction of the road. The second component is removing the soil or the materials from the ground for the construction of the road. For both components, we have to know the cross-section of the road pavement and also the terrain of the ground. With that, the cross-section is one of the most important variable we have to estimate for the earthwork. Usually, the cross-section will be determined based on the center line of the road. We need to specify the location along the center line and identify the cross-section at these stations. In earthwork, one of the most important operations we have to do is estimating the cross-section area. The figure here shows one typical cross-section area, which is a trapezoidal cross-section. The width of the pavement on the surface is set as W, and the width at the bottom of the pavement is set as 2D. Also, we define the thickness of the pavement as F, and the slope is set as S. With this information, the cross-section area is defined as F times W plus S times F. This one actually comes from the equation half of F times W plus 2D. These two equations are equivalent to each other. If the natural ground is not flat, then the equation in the previous page cannot be applied. In that sense, we need to conduct more measurements about the pavement thickness and the width of the pavement base. The figure here shows one example about the cross-section with a sloping natural ground. We need to identify the thickness at the initial point and the thickness at the middle point, also at the end point. And also we have to measure the distance from the initial point to the middle point of the pavement as dl, and the distance from the middle point to the end point as dr. Similarly, the width of the pavement surface is set as W. With that, the area of this cross-section can be estimated by the equation here. That is half of F times dl plus dr plus a quarter of W times FL plus FR. Sometimes the surface of the natural ground is irregular, and it could also be about the designed pavement surface. In that sense, we also need to estimate the area of the cross-section so that we can estimate the volume of the soil that we have to remove from the field. The figure here shows one example about the cross-section with an irregular ground surface. The width of the pavement is set as W, and we know the horizontal distance from the left end to the middle point as dl, and the horizontal distance from the middle point to the right end as dr. We also measure the depth from the natural ground to the left corner of the pavement surface, which is CL, and the depth of the natural ground to the right corner of the pavement as CR. With this information, the cross-section is estimated as half of CL times DL plus CR times DR plus C times W. For an even more complicated situation, we can actually apply the coordination method to estimate the cross-section area, which we have already introduced in the previous lectures. So assuming that we consider the cross-section as a multi-sided polygon and we know the coordinates of all the corners for this cross-section area. With that, we can apply the coordination method to find out the area as 1/2 of y1 times x2 minus xn plus y2 times x3 minus x1 plus until you have yn minus 1 times xn minus xn minus 2 plus yn times x1 minus xn minus 1. The details about this method can be shown in our previous lectures. Here, let's see one example for the estimation of the cross-section area. The figure here shows the information of this cross-section, and we are provided with the horizontal and vertical distances for each point. In this figure, the one on the top is the vertical distance and the bottom is the horizontal distance, which can be applied to estimate the coordinates at each point. In this example, there are 6 points. 1, 2, 3, 4, 5, 6. For the coordinates, we can have 1 as 0, 0, 2 as 3.50, 3 is 7.22, 1.86, 4 is 0, 1.11, 5 is negative 4.62, 0.56. As 0.5 and 6 is on the left side of the 0.1, so the x-coordinate is negative. Similarly, 6 is negative 3.5 and 0. Then we can call the equation in the previous page to estimate the area of the cross-section. With that, we have A equal to 1/2 of 0 times 3.5 plus 3.5 plus 0 times 7.22 minus 0.0 plus 1.86 times 0 minus 3.5 plus 1.11 times minus 4.62 minus 7.22 plus 0.56 times minus 3.5 minus 0 plus 0 times 0 plus 4.64, which will give us the cross-section area as minus 10.80 meters square. This indicates that we have to remove the soil from the natural ground for the construction of the pavement. The calculation of the cross-section area is one preparation for the estimation of the volumes of the earthwork. Once the cross-section area is identified along the center line of the pavement, we can then apply various methods for the estimation of the volumes of the earthwork in the field. The first method we want to learn is the average end area method. In this method, we have to know the cross-section area at the two ends, A1 and A2, and also the length from A1 to A2. With that, we can estimate the volume of earthwork as V equal to half L times A1 plus A2. Here, A1 is the cross-section area at the initial point. And A2 is the cross-section area at the end point. L is the centerline length from A1 to A2. V is just the volume of earthwork. We can also apply the Finite formula for the estimation of the volume of earthwork. In order to implement this method, we have to know the cross-section area at the initial point A1 and at the end point A2. Also, we have to know the length of the center line from A1 to A2. In addition, we need to identify the cross-section area at the middle point AM. With that, we have the volume of the earthwork as L divided by 6 times A1 plus 4 times AM plus A2. Here, the definitions of L, A1, and A2 is the same to the average and area methods. AM is defined as the cross-section area in the middle of the segment. The previous two methods are the approximation about the estimation of the volumes of the earthwork. If the road condition is very complicated and the ground is irregular, we have to introduce the finite element method for the estimation of the volumes. In the finite element method, instead of considering the initial and end cross-section area and the middle cross-section area, we will divide the entire segments into a lot of small segments with much shorter distance and estimate the intermediate cross-section area. And then we will apply the Finite formula or the average end area method for the estimation of the volumes of the earthwork. Now let's see one example for the estimation of the volumes of the earthwork. The figure here shows the settings for this example, assuming that the cross-section area at both ends are triangle. At the initial point, the base of the triangle is 30 meters and the height is 2 meters. At the other end, the base length is 15 meters and the height is 1 meter. We want to find out the volume of the earthwork for this segment with the length of 100 meters, which is from the station 0 plus 500 to the station of 0 plus 600. Now, let's see how we can calculate the volume of the earthwork with the average end area method. First, we need to find out the cross-section area at the two ends. At the initial point, we have A1 equal to half of 30 times 2, that is 30 square meters. And A2 equal to half of 15 times 1, that is 7.5 square meters. With that, we can find out the volume as V equal to 1/2 of L times A1 plus A2, that is 100 divided by 2 times 30 plus 7.5, that is 1875 meter cube. So that's from the average end area method. If we consider the second method, prismoidal formula, then we need to find out the cross-section area in the middle point. In this example, the base about the midpoint is half of 30 plus 50, that is 22.5 meters, and the height in the middle point is half of 2 plus 1, that is 1.5 meters. Then we can estimate the cross-section area in the middle point as half of B times H, that is half of 22.5 times 1.5, which is 16.875 square meters. We can then directly apply the prismoidal formula to find out the volume as L over 6 times A1 plus 4 AM plus A2, which is 100 divided by 6 times 30 plus 16.875 times 4 plus 7.5. With that, we can find out the result as 1750 meter cube. So the result is very similar to the average end area method, but both of them are the approximation about the volume of the earthwork in the field. So that's all about lecture today. Thank you very much for your attention. With that, we finished all the contents about the route surveying. In the next lecture, we will introduce the modern surveying technology.